Okay, so this is where we were yesterday, and I'm going to continue. So here's what we're going to do. Can anyone so ask yourselves this: what would have to happen to the currents that are passing into these three channels that I can actually get the action potential that is described over here? So what we are trying to do over here is now to look at the Hodgkin-Huxley from the conductance model's point of view, and try to understand whether we try to see whether we can explain the action potential in the Hodgkin-Huxley itself. What Siddhartha showed you was starting with a caricature model and asking whether we can describe a whether we can describe an action potential. I am trying to take a real model, a Hodgkin-Huxley model, and asking what would change in the Hodgkin-Huxley model to get the action potential, and then we shall merge it, and I will leave this as an exercise to ask you how do you match up the Fujino-Gumo equation and the Hodgkin-Huxley equation. So, what is the translate of the Hodgkin-Huxley into the Fujino-Gumo? Because the Fujino-Gumo is a two-dimensional model, you can understand it in the plane. Okay, that is why it is valuable. Anything in 3 dimensions and so on is much harder for us to understand. So, anything that is in 2 dimensions we understand completely, and Siddhartha showed you a good way of understanding what a 2-dimensional model can do. The question that I will leave you at the end of this class is, well, how do you translate a Hodgkin-Huxley model into a 2-dimensional model? Okay, the corresponding, which as Siddhartha pointed out, was actually carried out by Richard Fitzhugh and others. Okay. And then we will come back and discuss properties that arise from analyzing phase planes of models tomorrow. Okay. So, let us ask ourselves quickly, what would have to happen for the cell to depolarize? In terms of ions, I am now talking about ionic dynamics. Okay. So, can anyone guess what would have to happen? Again, we are talking of a we are looking at all of this retrospectively, all of this has been worked out, we know the equations, and now we want to make sure that we understand what the equations are doing. It is a 4-dimensional model. So, again you will not have a nice 2-dimensional picture to go along yet, but is there a way for us to understand the behavior of the 4-dimensional model to understand the action potential? So, what would have to happen? So, imagine which of these channels ought to open. You have got potassium channels in there, you have got sodium channels in there. Which of these channels, if they open and allow a lot of drain of that molecule of that ion, would it have to be the sodium channel or would it have to be the potassium channel? Thanks, Siddhartha. Sodium channel, right? Right, that is good. So, sodium was high on the outside, salt water, potassium was high on the inside. If the sodium channel is open, what would happen? Which way would the ions flow? The ions would flow inside. Now, because they are positively charged ions, if they flow inside the ion, that will raise the potential from negative towards a more positive direction, right. So, that would depolarize the cell. And what would have to happen? So, that would be the first phase of the action potential depolarization. What would have to happen for the repolarization to take place? Again, go back down.
Closing of sodium channels.
Closing of sodium channels could be involved, yes.
And then opening of potassium.
And then maybe opening of the potassium channels. So, so what would have to happen is we have to, in our equations, notice this behavior that there is an initial opening of the sodium channels, which causes sodium ions to run in, cause a depolarization. Then perhaps these sodium ions shut off, because we will ask ourselves why would they shut off, right? And the answer would have to be because the potential has changed, these ion channels change their behavior. Okay, it's at the top. So, let us look at this version of things. So, you have got resting potential, this is a balance between sodium and potassium, there is nothing going on interesting, there is no current that is driving the system, and so the neuron sits at rest. You notice immediately that EK is down here below the rest potential, right. Remember that I said EK was minus 80, minus 75, something like that, and ENA is maybe 100, 120. So, ENA is up over there, and the resting potential sits somewhere between these two and closer to the EK potential. Okay. If you wanted to see depolarization, the sodium channels have to open, that causes an initial depolarization. There is a little bit of a kink here, which I will leave you to understand. There is some sort of a thresholding going on over here, some threshold has been crossed over here. If that happens, there is a whoosh increase in the potential, I mean depolarization, so the potential increases, then sodium channels close, which means that this does not continue to go on. Notice you have reached very close to the sodium equilibrium potential, because this is where if all of the sodium channels were open all the time, then that is where you would land up, right. So, you head towards that, and if the sodium channels close, you no longer head towards that, or you slow down in heading towards that. Then the potassium channels open, which then brings down the potential, and in fact you come close to the EK. You have overshot your rest, you are coming closer and closer to the EK, because the E channels are open, the K channels are open, and then when the K channels close off, you get a refractory period and everything recovers, and it takes time for this recovery to take place. Okay? That is the basic broad idea of how this works. Okay. So, now our job is to see whether we can show this in the simulations that we are going to do. So, we have our simulations ready over here. Okay. We got to this point yesterday, right. I showed you this one yesterday, right. Okay. So, our job is going to be to understand whether we understand these components in terms of the simulation that is actually occurring. Okay. So, let us see, where should we begin? Any suggestions? I want to make sure that I understand the simulation, why it actually gives us the action potential. So, what should I look at? We have the basic diagram here. What would you want me to look at? Thresholding. Straight into the threshold, okay. Resting state, okay. What should I look? What should I check in my simulation to see whether I understand how the resting state appears? So, never mind the resting state, I want to understand this dynamic. I want to understand this, something has to change about the sodium channel. What changes the sodium conductance? Right. So, one of the G's are going to do this. So, GNA is going to change, and GNA is dependent on the gating variables. Right. So, which are the gating variables that are involved in the sodium channel? M and H, right. So, what do you think is happening to the M? Can you guess? Guess this ahead of time and then we will confirm it. Are you guessing or are you knowing the answer? M increases. Take a guess. What do you think is happening to the M channel? Okay, so let us do it. Okay, let us take a maybe we do not want to guess. Shall I try to line this up so that these two windows are exactly in the same place? And let me take a look at the okay. Here is what the M did. Can anyone explain this? And as a bonus, I will add H to this, and very usefully in a different color. Okay, so here it is, right? That is your M and that is your H. Can somebody try to explain this quickly, because we have to get through a lot of it.
Represent as they are opening up, and H represents the closing of that.
Yeah. So, how do we get to terms that this is what is happening? I am trying to give you a semi heuristic way of understanding what is going on in simulation, that you can actually get an action potential out of this. Okay. One of the things that we decided, or we sort of recognize in our analysis, is that there is a slight phase separation between the sodium and the potassium. Right, the sodium channels have to open first, and then the potassium has to do its own thing, right. Otherwise, you will, if they both do the same thing at the same time, you will not, they will cancel each other out, right. So, you need to have a depolarization phase which is essentially driven by sodium, and then you need to have this potassium come in. So, in fact, there is a name for this. It's the potassium channel current is called the delayed rectifier channel. It's built into the name that the potassium current is called the delayed rectifier. There is a small time separation between the sodium channel and the potassium channel, and that is very important for this phenomena to occur. Okay. Does that make sense? Okay. And so and there's a another component to this, which I will leave you, I will describe it to you and then leave it for you to try and figure out if you agree with this from the point of view of the simulations. There is a positive blowing up of the potassium channel current for the potassium current. It's as if there's a small amount of current that's injected in it, and that small amount of current then suddenly starts opening up more and more sodium channels, and the whole thing just blows up. That's why you get this high overshoot. That's why you get this very explosive depolarization. Okay, these are all interesting and things to see. You can see them in simulations. You have to spend some time over this to be able to figure this out, that this is actually correct. And not only is it correct, it's actually a essential component of what goes on. You have to have an explosive growth of the sodium current, and that's driven by the m cubed h component of it, right. So, I will leave that as an exercise. You maybe can take little notes down to say that, I should look for what m cube h is doing. What if I had changed this to m squared h? Well, change it in a simulation and see. What if I change it to m h? Well, change it in your simulation and see what would happen. This is a required feature. I mean, it's a feature, not a bug. Okay, it's built into the system. Okay, so now we realize that the m gate is opening and the h gate is opening, and we need to come to terms with why is the m gate opening and why is the n gate opening. Okay, I will leave as suspense for the n gate, for the potassium channel. We'll see that in a later simulation, in a little bit later. Okay, so let's try and see if we can understand what's happening to these. Okay, so I'll go down to a couple of more graphs that one can look at. Where am I? So, my scrolling down is deliberate, so that you can also follow which parts am I glossing over. Where's my here it is, which is the parts that I am looking at more carefully. Okay. In fact, a very nice reference to all of this, apart from this book, is a book that Sitabra briefly showed, Diane and Abbott. Okay, so let's take a look at this and see what this is showing us. Okay, so let's recall that my let's call it m dot is equal to alpha 1 minus m minus beta m, right. Okay, so I can call this alpha minus alpha plus beta m. Okay, yeah, okay. I can even pull out alpha plus beta. So, alpha plus beta, this is 1 of alpha over alpha plus beta minus m, right. Okay, so I am going to write this thing, and I am going to call this m infinity, and you will see in a minute. And so this is, and I am going to bring this down 1 over this. So, m infinity minus m divided by tau m, and tau m is 1 over alpha plus beta. Is that okay? Is my algebra okay? So, if you look at, and this is dm by dt. Now, let us take a look at this equation. So, m infinity is this blob over here, m infinity minus m, and I am going to pull this down. So, 1 over alpha plus beta, that is going to be tau m. So, now if you look at this equation and imagine for a moment that m infinity is a constant and tau m is a constant, right, then you recognize this is a linear differential equation, right. What is going to be the behavior of this differential equation from what Siddhartha, all of the machinery that he developed for you? M is going to track m infinity, right, because that is the fixed point of this equation. So, m is going to be dragged towards m infinity. If it is above m infinity, it comes down. If it is below m infinity, it goes up. So, m is dragged to m infinity. What is the rate at which it is dragged to m infinity? Tau m. Okay. Got it? It is a nice and quick and dirty way to see what is going on. Okay. Now, let us imagine what, now let us see what m infinity actually is. M infinity is a function of v, and tau is a function of v. Okay. So, what does that do? Let us take a look. Okay. So m infinity is a function of v. This is v, this is m infinity. Okay, it's written m, but it should be m infinity. Yeah. Okay. So can you look at this graph and tell me what's going to happen if the voltage changes to a positive value? What happens to m infinity? If the voltage changes towards a positive value, m infinity, it becomes closer to 1, right? So m, the variable m will get dragged towards m infinity at a rate tau m. V, it's so m infinity in this case is actually dependent on v. Okay, shall I make it more explicit by saying this depends on v and this depends on v as well, functions of v. Okay. So m, as the voltage is depolarized, the target m infinity is also becoming higher. Now can you see why m would start to go up in my simulation? There is one component to it. We still have to worry about what about tau m, right? Okay, so in this case tau doesn't change very much, and notice that tau is small. So if tau is small, what does that teach us from that equation? M is going to get tracked to m towards m infinity quickly, right? So nice, and it doesn't change very much. Let's ignore the dependence on v. So let's just say it's low and small. Okay, good. So if m infinity changes from a low value to a high value, that is saying to us, and why would it change to a high value? That's the depolarization, right? That says to us that m gates are starting to open up. M is becoming 1. If m is 1, that's the fraction of gates open. So more and more gates are opening up. Got it? Now do we understand why the sodium current starts to flow? Yes or no? I think I have all the pieces in place to convince myself, at least in a heuristic sense. Now I understand, I think, why m starts to open up as the voltage depolarizes. Does that make sense? Okay, all right. So then the second component to it, this is the ball and socket model, or no, sorry, a channel, a pore with a ball in it, right? Okay, the second component of it is h, which was open, actually goes down to 0. It's m cubed h. So if m is open but h is close to 0, the whole product is 0, right? So if the h starts to, as depolarization occurs, h comes down, h infinity comes down, the ball starts plugging up the channel, the sodium channel, correct? Okay, so why doesn't that cause us a problem? Why does the current still go up? Yeah, it inhibits, right? So why does that not prevent the sodium channel from going up? That's right. So the time constant of h is much higher. Never mind the variation in v, you can work on it at a later stage, but it is at a level that's much higher than m. So whatever happens to the h gate is going to take place on a slower time scale. So it opens first and then it closes. Got it? So the opening is actually opening of the 3 channels up, then with a little slower time scale, the ball comes in and plugs the hole. Okay, so there is room for the sodium channel to rise. Okay, so now that we understand this, so now we understand both components of both the h, the m going down and the h going up. Now we have to explain this part of it. Okay, so can you from these figures now guess for me what is happening to the potassium channel? The potassium channel was n to the 4th. What do you think is going to happen? I imagine an equation like that written for n, excuse me, for n, and tell me what happens. What's likely to happen, and then I'll do the simulation and show you what the curve is. Just walk through the logic exactly as we did for one of these gates. Come on, don't feel shy. I have a lot to cover. So the end gate is, so the voltage is increased. You're on that side. What happens to the end gate?
starts opening.
The N gate will open up, right?
Yes.
Okay, and it's happening on a time scale closer to H than M. Okay, so the potassium channels are open now. If the potassium channels are open, that will depolarize the cell. The sodium, the M infinity time, the time constant of the M gate shows you that this is the first thing that will happen, and almost on a similar time scale, N and H gates will change. If the H gate changes, that shuts off the sodium channel. If the N gate changes, and we are high because they are depolarized, the N gate responds by opening up slowly. If it does, then you get depolarization again. Okay. So, by a coordinated movement, the sodium goes push, then that gets blocked and the potassium channel comes in, you get an action potential. Does that make sense? Okay. So, let us confirm it. So, try and guess what the curve is going to look like, and then in a minute I will plot it. Okay. All right, I will give you 15 seconds to think through, and then I am going to plot the. So, what do you think the end curve will look like? Guess it. If you guess it right, you will have understood it, at least in the sense that we understand a 4-dimensional model. Quickly, before I click OK. Which of these two curves will it look like? Some say black. Will it look like a black curve, only pushed out? Okay, so take your guesses, and here's the answer. Right? Did you get it right? Does it make sense? It has a time scale that's corresponding to the H gate, that's closer to the H gate, and has a dynamic that is similar in the sense of opening and closing, similar to the M gate.
So the coordination between opening this ion channel,
Yeah.
it is solely based on fast opening sodium,
Yeah.
and slow opening potassium.
Absolutely.
Only the coordinating.
Yeah, that's the beauty of it. Yeah. Yeah. So, for those of you who want to know more about this, there is actually a nice Macarena dance that can be done in this due to Jim Keener, and if I can find a YouTube video of this, I'll share it with you. It's this coordinated dance that allows you to get this. If you break this coordination, things will not happen. And you can play with this in the file that you have. You can choose to what would you change? Well, change the sodium current. Change the sodium current by changing the time constant of the sodium tau m multiplied by a factor of 4. Okay, lift everything up. See if you get the action potential. Yeah, correct. So, these are voltage gated channels. The subunits are voltage dependent, their dynamics is voltage dependent, correct? Yeah. So, that is what causes all of this to happen at the end of the day. Yeah. Okay. So, that is the origin of the memristor in the Hodgkin-Huxley equations. Any questions? Are we comfortable understanding what causes an action potential? What causes an action potential means you have to explain the depolarization, repolarization after hyperpolarization. Those 3 phases. That's where the gold lay at the time of Hodgkin and Huxley. Cole couldn't do it. Bernstein couldn't do it. Hodgkin tried. Hodgkin and Huxley together finally got it. Right? And this is all happening at the time. When was the Nobel Prize? 1964-ish. Homework for you, figure out when the Nobel Prize was. Nobody knew about ion channels at that time. Amazing. So, a brilliant piece of work, right? It's where we are, in my mind, it's where we are with neural networks, with CNNs. We have it, we have the equations, we don't know what's going on, so we have to figure it out. So, they had the equations, they figured it out, they could understand that there was something happening along channel lines. It's like ants carrying sugar bags on their shoulders. They knew something like that was happening, but they worked out the detailed maths of it, and much later, I think it was almost 2 decades later, that the first channels were crystallized. Okay, so this is what I want to say about the Hodgkin-Huxley model. Okay, we'll have more to say about this, but I'll leave it as a homework for those of you who are interested. It's not quite a homework. It's you can look it up or you can think about it and then come and ask one of us. How would you go by taking, in terms of taking a two-dimensional model, sorry, a four-dimensional model and converting it into an equivalent two-dimensional model? There's a formal, not formal. There's a set of clever tricks one can do to convert it formally. Okay, an equivalent this thing, and then you can understand a two-dimensional version of it. Okay, so now I want to, any questions? Yes, please. In simulations? Okay, so what you, so I created this new window by going to M is where? M is. So you see these capital letters over here? If you just click that letter on your keyboard, that's a shortcut. Okay. So make create. I can't find it. Where is it?
Make window and then create.
Okay, make window and then create it. Fine. So that's how you create this window, and then do graphics add. Okay, and you can keep on adding stuff into that. If you still can't get it, at 6 o'clock when we meet, whoever wants to meet at 6 o'clock, which room are we meeting in? We are meeting in, this is the floor, right? This is the floor all the way down to the left. Yeah. So that's, it's one room below where we met for the mixer yesterday. Okay, so I'll be there at 6 o'clock today. So 5 to 6 is your meeting. I'll be there at 6 o'clock. Whoever wants to do this in detail with me, like if you have trouble in XBP and you want me to show you, I'll be there to show it to you. Okay, so this is what I want to talk about for the Hodgkin-Huxley. So now I want to show you how to connect two Hodgkin-Huxley neurons together. I want to build the simplest networks for you. Okay, so where will we begin? Let's ask ourselves, how should we model? We will come back to this. We will come back. I'm not quite done with Hodgkin-Huxley, right? I'll show you. I want to show you behavior of the Hodgkin-Huxley models also for different. So Sitabra did this nice little exercise for you, where you can have 3 fixed points, or you can raise this and you can get say lower it and you can get 1 fixed point, something like that, or you can raise it and so on. You can get various behaviors, including a fixed point or an oscillator train and so on, and I want to show you that you can actually get all of that in the Hodgkin-Huxley model directly by simulation. So I want to show you the simulation version of these things. Okay, and again, like Sitabra said, we are going to change current to see this. Okay, so for example, I can take this just as a teaser. Let me try and inject some current into it, say 5. Okay. And there you go. I suddenly have oscillations in my model, right? So by injecting a small amount of current into it, you got a train of oscillations. You don't believe me? Okay, there it is, right? Again and again. So I can continue this for a longer period of time. You got many more oscillations. Okay. Okay, so I want to show you behaviors of this type, which I will do in a bit. But first, because this is because we are very interested in networks in this workshop. So I want to show you how you can connect neurons together. Okay, so let's ask ourselves what's going on when you have my very poor drawing of a synapse. So neurotransmitters this is the presynaptic side, this is the postsynaptic side. We are going to have to explain transmission in a way that what we need in our model is going to be a current injection corresponding to the synapse, right? So in order to describe how neurons will couple, I need to have a presynaptic neuron, I need to have a postsynaptic neuron, and I need to be able to say that if this presynaptic neuron spikes, that causes something at the synapse, which then causes, may or may not cause, some response in the postsynaptic neuron. Okay, so I need 3 components for it. I need to be able to have a V presynaptic side, I need to have some release of neurotransmitter, I will call it T for example, and I need to have some variable which corresponds to the synapse dynamics. I will call that S, the degree of activation of the synapse itself. If S is high, synapse is active. If S is low, the synapse is inactive. Something to say that the synapse is acting now, and then I have to have something on the postsynaptic side. I have to correspondingly the synapse should initiate or at least it would stimulate it, whether or not causes an action potential is a different matter, but should stimulate by injecting a current into the postsynaptic side. So, can you guess for me what you would do for the I have C dV dt, C dV dt is equal to a whole bunch of ionic currents, right? I k plus I N A, I leak, all of that stuff, right? So, can you guess for me what I would do in order to simulate that this should also be simulated by a presynaptic neuron?
What is the ID?
Oh, this I mean bad handwriting. I L I K I N A. This is the standard Hodgkin-Huxley equation. I am ignoring the gates for the moment. This is the postsynaptic neuron. What should I do to stimulate it with an I synapse? Can you guess a form for this? What if just like we have had other equations, what if I take G sin, and this comes with a minus sign. If you like, I will put minus signs over here just to make it homogeneous, but you know what that minus sign means, right? The V should have a minus sign on it. Okay, now see if you agree with me that that is an appropriate term. Just like we had a reversal potential for the sodium channel, for the potassium channel, I also have a reversal potential for the synapse. Okay. So, this is my synapse reversal potential, that is my voltage on the postsynaptic side, same thing over here, right. It is driven by some constant current which represents the strength of the connection, right, and this is the variable that corresponds to whether the synapse is active or not, right. Does that make sense? Okay, good. So, now I need to write down an equation for the synapse. Shall I model it after the opening and closing of gating channels, right? Okay, so let us do that. Yeah, makes sense. So, I am going to have some alpha, some number, some rate 1 minus s minus beta some rate s, okay, except I need this coefficient to have a very special behavior. It should do the following. I want my S, whenever the presynaptic side fires, I want my S to go up, and then once the presynaptic potential passes through, well, then the neuron can, then this S can come down. Okay. The coming down is taken care of by this. So, all I need is that this should be driven by transmitter, and the transmitter should drive it up. Okay. Does that make sense? So, the transmitter will go up when the presynaptic neuron fires. So, essentially I want this rise phase to be determined by a presynaptic voltage firing. Presynaptic fires, that releases transmitter, transmitter causes this alpha to go whoosh up. If it goes up, this S starts tracking that very quickly, and then it decays with a certain time constant once that transmission is gone away. Does that make sense? Is this basic equation clear? All variants of the synapse are going to have this basic form with certain additional bells and whistles thrown in. This is determined by V pre. Okay. So, the catch, so what you should catch here is this change, this rise should be determined by the presynaptic voltage firing. The decay is on its own once the presynaptic voltage has passed right through, it just decays at some rate constant, right. In the equation for this, is this V pre, this V, is it V pre or V post? Louder please. V post, that is right. So, this is post synaptic neuron. Does that make sense? Everyone agree? So, now we have a framework in which a presynaptic neuron causes this to be driven up, this is S as a function of t. Once this is driven up, the presynaptic stimulation is free to pass through, go away. When it goes away, this becomes 0, but S is stuck up at a high value because of this action potential from the presynaptic side, and once this goes away, it is free to fall off with minus beta. Okay. So, there is going to be two components to the synaptic variable. The first is driving up very rapidly for a V. So, what does V pre do in our network? It sets the timing of when the presynaptic neuron fires. Whenever the presynaptic neuron fires, S is driven up. If it fires again, S is driven up again. Okay. And this is an intrinsic decay constant. So, you can have fast synapses which last a few milliseconds, or you can have actually slow synapses which last several, perhaps even 100 milliseconds. So, a lot of the work that is done in computational neuroscience is to try and understand what is the difference between having a fast synapse or a slow synapse. You understand where fast and slow comes from? It is coming from this, from changing this time constant, at least at an essential level. There will some of the, I will show you some of the equations, some of them can be a little bit more complicated, but whatever it is that decay constant of the how long does the transmitter decay through, what time, what rate does it decay with. Okay. So, this is going to change your fast or slow. So, in your networks, whenever you want to simulate stuff and ask how can I, so here is an important question, okay, from the point of view of those who are thinking of projects. Okay. Neurons work on a couple of milliseconds time scale. Okay. We saw that, for example, a single neuron has I turned it off, but it had a couple of milliseconds, maybe a 10 millisecond width of the action potential, right. Can you get anything slower than that? Can you get behavior that is slower than that, and can you get behavior that is faster than that? How would that be possible? Say what? Somebody said something. See, think about it. Your action potential is basically just a quick jerk, right? Okay, the only thing you can worry about is whether this comes once or twice or 3 times. That's all you can worry about, right? How can you initiate something that lasts for 2-3 minutes? You just have to keep tapping for 2-3 minutes, right? That is not the only way things work. So, understanding time scales, how can slow processes be driven by something that has an intrinsic time scale that is fast? Where does it come from? Could you get it by coupling neurons in a network somehow that activity in the network takes a minute to come around? Could you? Yes or no? Okay, try it. It is not easy. Okay? Then you start to appreciate how things like calcium become important. So Upi showed you all these lovely scales from the molecular through calcium, through mitochondrial to but the ionic channels sit somewhere in the middle, 5, 10, 50 milliseconds. Challenge yourself to ask yourself, if I couple 2 neurons, and I will show you in a minute a simulation of a neuron coupled. If I couple myself to another neuron, the first neuron is firing at a certain rate. Can I control the rate at which that neuron fires? Can I control? So, if that is the case, then it would be a firing rate model. That means the activity is not in the essential information is not in the spike itself. It is how fast the neuron fires that causes the effective information. movement of information. So, what would you do to control the rate at which neurons fire? You have all the equations, now play with them. So, tell me what you would do. I want to change the neuron firing from a certain frequency, I want to double it. I want to double its frequency, or I want to halve its frequency. Can you do it? Okay. So, let's think about it. I'll give you an answer today. But remember, the questions that I am asking are the following: can the network operate at time scales that are different from the time scale of an individual neuron? Can the network be faster than that? Can the network be slower than that? How can the network be faster than that? The activity hasn't even completed. How can the network be faster than that? Can it? What's the answer? Somebody said something? But it can. Okay, so think about it. These are questions to think about. How would it do it? You need to react at rates that are faster than the firing of a single neuron. Waves, auditory waves. Do you think they have a frequency that's faster or slower than a single neuron firing? What is the frequency of an auditory wave that is relative to the frequency of a firing train, of a firing neuron potential train? So, work it out. At what frequency do we hear sounds? What is that frequency? And can a neuron fire at that frequency? Don't nod your head. These are questions that you must answer from simulations. Okay? You can speculate, that's good, that's raising a hypothesis, but then come up with support of this in a simulation, right? So, I am giving you questions that you can think of for doing a project. How can you possibly get something, an activity that is faster than the firing of a single neuron? A single neuron will not have finished firing. How can you get something that is faster than that? But my clue to you is, think about what is the frequency of auditory responses. How fast do words come to our ear, right? Okay, so that is one question that I will leave you with, right? So, I'm posing a couple of questions, some of which I'll answer in a minute. I want to be able to tune how fast a firing can take place in a neuron. What shall I do? Okay. Second thing is, if I were to couple them, how should I couple them so that I can get activity that's faster or slower than the rate at which the neuron itself is firing? Okay, so we will need to get into networks. Okay, so now let me go to this chapter 7, and I'm going to show you the equations that I was working with. So, here it is. So, that's my equation for the the synaptic current. That's going to be some conductance of the synapse into V post minus the V reversal potential, right. This is the reversal potential of the synapse, this is the V post. Okay. So, I am going to skip through all of this, you can read it, but I think it is best done if you first read ahead and then come back to understanding what this is. If you try to go through this, you will stop there. At least I find it difficult to go through all of this. I already know what is going on, so I can read it, but I think it is very difficult from a teaching perspective to go through equation 7.4 first, because the real equation I need is 7.5. Okay. So, this is my equation, right. This depends on the neurotransmitter driven by the presynaptic side. Okay. So, what I need now is an equation that says if the neuron fires, then the transmitter should go up, and that is not a very difficult function. So, this is all showing you what the solutions of these things are. I have already done that for you. That is the equation that we need. So, the neurotransmitter driven by the presynaptic neuron as a function is going to have this 1 over 1 minus exponential function. Okay, let me give you a sense of what this function is. It looks bizarre when you just see it at first, but it is actually a very wonderful function. It is a lovely function that you can tweak and twist in all sorts of ways. So, 1 over 1 plus exponential minus V. If I were to plot this function as a function of V, can you think what it might be. What might be? If V is negative, what will happen to this? Somebody said it right. What is 0, right? Yeah. So it's going to start from 0, and if V is very large, what is it going to be? 1, right? Yeah. So somewhere down in between, this turns across, right? So that's a nice function to play with. Okay, if I stick in, what's the way to do it? Yeah, V minus V threshold. What do you think I'm doing it if I do this? Huh? Somebody said it right. What was it? Whatever this inflection point was, I shifted to V threshold. VT, H, yeah, maybe. No, it uses T, I'll write T. Got it? So this adding this shifts the origin of V to V threshold, right? And then if I stick in, what is it called? Vs. Suppose I stick in Vs, what does that do? It will change the steepness of this, right? That's it. That's what you're doing. Okay. So if you implement this function, okay, I'm going to, because in the interest of time, I'm going to leave this as an exercise to you. Do you think with all of these equations and Bard's notes, can you implement this yourself? Yes? Okay, I'll show you what the solution is and then you go and implement it. So I should tell you a little bit about excitatory and inhibitory synapses also. So as the name suggests, an excitatory synapse is one where if the presynaptic neuron fires an action potential and it couples to the postsynaptic side excitatorily, then this guy gets excited as well. This guy is more likely to fire. If it's inhibitory, then when the presynaptic neuron fires, this is less likely to be excited. It gets inhibited, right? So that's what inhibited and excitatory neurons are. There's various kinds of inhibitory and excitatory neurons. So fast synapses, there are two major kinds. AMPA kinase is an excitatory neuron, is a synapse, and GABA A, for example, which is a glutamatergic neuron, is inhibitory, right? And then there is correspondingly slow synapses, which are NMDA type, and GABA B are slow synapses, right. So all of the equations of these are in Bard's book. Because I don't have time to show you all of this, I'll just refer you to the book and you can play around with these things. These slow synapses are a little bit harder to, they're a little bit involved, but I've shown you the basic principles for how you can get these things. There's a nice trick you can use. You can take the equations of the fast synapses and just elongate the change the beta over there, just elongate the synapse, make it 100 milliseconds, right, and you will get a slow synapse. If you wanted to just hack into the whole thing, just take a fast synapse and stretch it out. Okay. So that's one way to do it, but to do more reasonable, more professional work where you want to actually use the dynamics of the kinetics of the NMDA receptor, use the equation of the NMDA receptor that have been worked out. I'll show you in this what I have done, and then we can take a quick look through this, what this does for us. So there are two neurons. Okay, this is my neuron 1 and this is my neuron 2. So just for the just for checking things out, I actually developed this code in was it Grok? No, I used DeepSeek to do this. Okay, I gave it my Hodgkin-Huxley file. I uploaded it and I said make 2 neurons for me and couple neuron 1 to couple neuron 2. It got it wrong. It messed up the code in all sorts of ways, but I was able to clean it up in a way that it saved me some amount of writing. Okay, so let's go through this. This is, I'm labeling all my neuron 1. So these functions are going to be the same because I'm taking 2 identical Hodgkin-Huxley neurons, right. So I can just write this once, right, and then so very helpfully DeepSeek put this label over here, shared. Okay. So this is neuron 1, this is neuron 2. Do you agree that I have 2 neurons reasonably placed? So I have 2 neurons identical. In second neuron, I added my current, synaptic current. Now, am I right in saying this should be V2 or should it be V1 over here? That's a synaptic current. It should be V2, right? The postsynaptic side. Okay. Now, S should be 1 or 2. 1 stands for the first neuron, 2 stands for the second neuron. So, S1 should be the synapse from the first neuron, right? So, I made it S1. Okay. Now, if I look at S1, the equations corresponding to S1 here, have I written it correctly? I don't know if you can read down below here, maybe I will pull this up as far as it can go. So, this is my S1 driven by an alpha times 1 minus S1, and this is my T function. Okay. The T function is just a switch, right? If the voltage is low, it stays low. If the voltage is high, it switches high. Okay. So, the interesting thing is going to be what this threshold is going to be, right? Okay. So, in this case, the ampere, if you have an excited neuron, is going to have a reversal potential equal to 0. I did not put in for the GABA, I should change it and show you the GABA. So, the GABA is going to have a lower reversal potential. Okay. So, if my reversal potential for the synapse is high, 0, then that is where the synapse will not draw any current, right, B minus V synapse. So, that means the neuron will be driven up to 0, right. If my potential is low, then the neuron is not driven up, it is actually suppressed. Okay. So, that changes the, and then you have got minus beta 1. Okay. So, is everyone okay with this equation? This is the equation for, and which neuron will drive this? If my presynaptic neuron is V1, should I have V1 here or should I have V2 here? V1, correct? Okay. So, those are things you have to catch. DeepSeek will mess this up. Okay. So, you have to know what you are doing, because if you get this wrong, everything is wrong, and DeepSeek actually got it wrong. Okay. So, you have to know what to edit and why it is being done. Okay. Okay. So, I will leave this with you. I will post it. I will send it to Sitabra across and we will post it. You can play around with this and you can try and see if I have my equations right. If I have my equations right, an action potential train in the first neuron should actually excite the second neuron. It should make it, it should boost the second neuron. Isn't that right? That is one quick sanity check to see whether I have the equations set up right. So, I will leave this to you to check. I checked it last night, I think it works, but if it is not, well, point my mistakes to me. As I said, it is a hybrid of DeepSeek and me. So, maybe you have got something else wrong. Okay. So, I will leave this for you to check. Okay. The next thing that I want to do before I close is I want to show you what the behaviors in a Hodgkin-Huxley neuron are. So, Sitabra told you that you can get a train of action potentials, you can get stationary points, tetanic stimuli or completely stationary. So, are all of these behaviors possible in a Hodgkin-Huxley neuron? Yes, they are. Okay. And the other question that I asked you, what will you do to change the rate at which the Hodgkin-Huxley neuron is firing? Answer to that is, what variable will you alter?
Relaxation time needs to be seen. The refractory period. So
Okay, you could do that, yeah.
fire again.
But is that what is that?
The current,
I mean, do you think
input current.
input current? Yeah. So in a neural network that's functioning, it's presumably the input stimuli, and the input stimuli is current typically. You're not remodeling the kinetic parameters of the neuron all the time, right? So what changes is the input. The input is the input current. Okay. So what are some of the behaviors? So if I ask you, your neuron is firing at 10 hertz, make the neuron fire at 20 hertz, precisely 20 hertz. What will you do? Can you find out how much current is needed to make it fire at 20 hertz? If that was the experiment you wanted to do in simulations, what would you do? Well, you'd have to know a couple of things. You'd have to know whether or not the neuron is capable of firing at 10 and 20 hertz in the first place. And if it is, then just tune up the current low or high until it starts firing at 20 hertz, right?
Can make the neuron fire at that frequency. Again, refractory period. By tuning that, you can just
Yeah, I'm being very pragmatic. I'm just saying, tell me what current I need in order so that the neuron should fire at 20 hertz. Right? So there are these things, I don't know if Sitabra will cover it or not, there are these things called alpha waves and beta waves and things like that. There are typical frequencies at which our brains operate in many conditions. So you need to know what is the effective current that is getting into a neuron so that it fires at 20 hertz. Okay, so let's ask ourselves whether you can do this. So I'm going to show you how to do this in code. Okay, I'm going to fire up my Hodgkin-Huxley neuron, and what I've done in this is that stimulus that I had, I dropped it. I'm going to only retain a tonic component, a DC component of current. Okay, so I'm just going to say I0, and that current is going to stay on for the whole time. That pulse that I had, I got rid of the pulse. Okay, so I want to know if I inject current tonically. Tonically means at a constant rate, at a constant level. If I inject current tonically, what is going to be the response of my neuron? That's what I want to know. Okay, I can do experiments, and you should. If I inject 4, what will happen? If I inject 5, what will happen? Okay, so let's do that. I mean, if I inject current I0, let's say 10, what do you think will happen? Well, you can't know, right? So just do the experiment and see. So it fires a train. But does it also mean that if I inject 20 now, 20 milliamperes, it will fire at twice the frequency? How many people say yes? Almost nobody, right? So everyone recognizes that neurons are nonlinear. So just by doubling the current, it will not necessarily make the neuron fire twice as fast, right? Okay. So now I need to ask, what is the range over which I can inject currents so that I can make the neuron go at a certain rate? Can anyone guess ahead of time? Well, if you can't guess, we'll do the simulation. There's no reason why you should be able to guess. Okay. So let's go back. And these are the steps that are required for you to compute what's known as a bifurcation diagram. A bifurcation diagram is a map of all of the behaviors possible of a neuron as you sweep current. So given a certain current, what is my behavior? Given another current, what's my behavior? Given another current, what's my behavior? That's what I'm going to do. Okay? Everyone understand that? Alright, so let's do it. These are the steps. If you follow this, you can do this yourselves. So I'm going to change my current to 0. Okay, I'm going to do a simulation. Now I'm fit this, and I don't get something which is flat yet. So I'm going to do initial conditions last, which means I take all of those values, put them at the beginning, and then run again. So I'm going to do this a couple of times, and you will see that I settle into a steady state. Okay, so initial condition last, that's what I get. I'll do this a couple of times just to make sure that I have settled into a fixed point. All convinced? I did this a couple of times, so I'm at a fixed point. The fixed point is 65. Technically, I should also check that the M and N and H are also at fixed point, but I've already done that once. So I won't do this now. So if all these are stationary in time, that means I'm at a fixed point. I need to start with a fixed point for what comes next. Okay. I'm going to open up this thing called file, and then I'm going to click on this program called auto. Auto is that miracle program that's going to help us produce bifurcation diagrams. Okay, so first thing I do in auto is go to this and set up my parameter. My first parameter, ignore the others. My first parameter is I0. That's the one that I want to change. So I'm going to say I'm starting with I0 equal to 0, and I'm going to change it. I'm going to change it 10 and then 20 and 30 and 40. Hey, why don't you just do the whole thing in one go and tell me what it is? Okay, all right. So I will do this. I click OK. Then I get to the next block, axes, high, low. Okay, there's a whole bunch of other things. Don't worry about it. Cancel away. Then I go to the next block. So I'm just going through these blocks one by one, right? The auto is like a stick shift Ferrari. If you know what you're doing, you can go very fast. If you don't know what you're doing, you can go into a ditch very fast. So watch what I'm doing. This is the best version of doing auto. So I'll go to numerics. I won't change much. Okay, let's just change these two things: parameter min and parameter max. Parameter min is starting from 0. I'm going to take the current up to say 200. It's going to sweep through all values of current. Okay. There's a couple of other things. If anyone's interested, you can talk to me about it. But these are involved things, so not straightforward to describe in the first go. Okay, so I'm going to sweep. Do you see everything, everyone? I'm going to go from between 0 and 200. That's all I change. Okay, and then I'm going. Let me start. Okay, so here's the run part of it. I'm going to run it, and I'm going to pull steady states. I started with a steady state at 0. So that this is asking if you were to change the current from 0 to a little bit more, what happens to the steady state? So try dragging the steady state. So if at a nearby value 1 of current, you get another steady state. Okay, you've drawn what the new steady state is. At 2, what's the new steady state? At 3, what's the new steady state? So give me this curve of steady states. Okay, let's do that. Okay, nothing happened, but that's okay. We know that that's just because I was looking in the wrong place. So I fixed the viewport, and here's what I get. Starting with 0 and going up to 94. I know it's not gone up to 200. I will get to it. It's gone up to 94 because it ran out of memory and whatnot. Okay, it gave me a branch of fixed points. Okay. What this bit is, it's actually stable fixed points. In this bit, the one that's in black are unstable fixed points. You have fixed points, but they're unstable. Can you guess what would happen if there's an unstable fixed point in the Hodgkin-Huxley? So if I turn up my current to say 50, that's what I'm going to get. It's an unstable fixed point. So what do you get?
Come back.
Huh? Come back to what?
Limit cycle.
Maybe you'll get limit cycles. Yeah. Okay. Let's check. So just to complete this diagram, I needed to go up to 200. Yeah. It's gone only up to this thing. So I'm going to do the following. It ran out of memory. I didn't change it because it was a little bit involved. I want to show you what happens if you run out of memory. So I'm going to click on something called grab. Okay. So this thing grab, I'm going to click on this. If I do that, a little cursor appears here. And now I can move this cursor, tap, 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 all the way to the end. And I'll say OK, and I'll just continue forward. Got it? Okay, so watch. I'm going to say tab, 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 all the way to the top. Now the cursor is moved up here. Now I'm going to click enter to say grab this point and continue further. So then let's see if we can continue further. I'm going to click on run. And let's see if it has done anything for us. Yes, it has. Okay. So I get a stable branch, an unstable branch, and a stable branch again. What do you think is happening over here at this point 10? If I were to ask you what is the behavior of this neuron at point 10? By the way, it just puts arbitrary knots along this. So 1, 2, 3, 4 are just arbitrarily placed as far as.
Is that the tectonic?
Yeah, that will be technique stimuli. Yep. So the neuron will get frozen. It's like you shocked your heart to pull yourself out of a heart attack, and you give it such a hard shock that it just froze in place. Okay, so we have this. Now let's ask ourselves, what can we do more than this? Okay, so I'm going to grab again, and this time I'm going to stop it 2. This is the threshold. So this is the critical point in going from a stable to an unstable branch. Actually, there is a nice little thing that appears over here. It's called HB. For those of you in the know, this is called a Hopf bifurcation. Okay, so there's a Hopf bifurcation point at 2 over here. I'm going to grab this. Grab it means I'm going to enter it. I'm going to catch this point, and I'm going to ask. Let's ask what happens So it's a Hopf point. If I see a Hopf point, I expect around that point to have periodic oscillations. Okay, and I'm going to click on run, and I'm going to say periodic because I know it's a Hopf point. Okay, something has happened. Again, I get something. Okay. So it turns out that I get a whole branch of periodic orbits. For every value, this is the top point of the period and this is the bottom point of the period. It's not very clear here, but I'll show it to you when I zoom in on this. I'll show it to you. Okay. The reason why they are open blue circles is these periodics are actually unstable. Okay, what's going on? You got an unstable branch of fixed point. You got an unstable branch of periodics. What the hell? Something's wrong, right? Okay, so let's go to the other side. I'm going to grab this point over here, right, where this unstable turned into stable. I want to grab this one. What is it? What is it? It's a Hopf bifurcation point. If I have a Hopf bifurcation point, I expect there will be periodic orbits in this region. Okay? Okay, I click enter. I'm going to click numerics and I'm going to change the sign to be minus this so that I'm stepping backwards. You'll see in a minute why I'm doing that. Again, I'm going to click on run and periodics because it's a Hopf point. I expect periodics around it. So I want to see the structure of those periodics. Okay. There you go. You get a branch of periodic orbits coming out of this Hopf point. And now it's clear that if I were to keep my I0 here, that's my high point of the cycle and that's my low point of the cycle, the up and lower part of the amplitude. Okay. So you're going to get at this value, you're going to get an oscillation of this size. The voltage will oscillate between these two values. If you want an oscillation with a larger amplitude, turn down the current. Right? If you want an oscillation with a very small amplitude, bring it over here. You'll get a little ripple of an oscillation. Okay.
Blue ones are also supposed to look like a pitchfork, right? The blue part.
So this is not a pitchfork; it's a subcritical Hopf.
Hopf is a projection of pitchfork. There's something.
Let's discuss that later.
Sure.
I'll finish this and then we'll talk about it. Okay. See, I'm moving my cursor around because I want to get to this end. It didn't quite complete. I think it just got ran out of memory or something. So I want to complete this. Okay. Let me grab that point and run more, and I'll use extend just like you used it last time. Okay, that's my diagram. Okay, so you see a number of interesting things that are taking place over here. You had a branch of stationary points or fixed points. That branch became unstable in this region, and when it became unstable, there's actually a branch of periodic orbits that rises in place. Okay. There's actually a very interesting region right around here, and I'll leave it for those of you who are interested to figure out exactly what's going on over there. Otherwise, it's a bubble. It's basically a bubble. Fixed point if your current is very low, fixed point if your current is very high. In between, you largely have unstable fixed points, which means even the smallest perturbation will just take you away from that fixed point, so no fixed point. Instead, you have a branch of stable periodic orbits. And something very, very interesting happens over here. With those of you who are interested can come up and ask me, or you can try to figure it out. Okay. So this gives me a map of all of the behaviors that are possible in the Hodgkin-Huxley equation if I were to change the tonic stimulus current. This gives me in a direct manner what are the behaviors possible. Now I can start asking questions. Should we break for lunch?
I think even though
Yeah, maybe we should break for lunch. I'll ask yourself this, I'll leave it as a homework exercise. What frequencies are possible? I didn't show you frequencies here, right? So there's a small step going after this, which can actually tell you what the frequencies are. This diagram doesn't tell you what the frequencies are, this diagram tells you what the amplitudes are, but the question I was asking you, can you change frequency of a Hodgkin-Huxley neuron? So those of you get to this point will have a reward at the end of it. If you can get to this point, I can show you what frequencies are possible in the Hodgkin-Huxley equation. Do you think every frequency is possible? No, right? There has to be some band limited region. Yeah? There has to be some range of frequencies that are possible in the Hodgkin-Huxley. What is that range? Is it good enough that you can actually hear with the network of Hodgkin-Huxley neurons? Okay, so I'll leave it to you. Okay, all right. So let's stop here and get some lunch.